3.8 Applying the energy balance using property tables and software. In this class, we are not going to use a computer software to determine thermodynamic properties. In these sections, we are going to determine the thermodynamic properties of substances using property tables and apply the energy balance relations for closed systems. Energy balance equations simply state the conservation of energy. Closed system indicates there is no mass crossing the system boundary. The energy balance relations for closed system is expressed here. Generally, the energy change of a system is denoted by delta E. And the delta E include the change in internal energy and kinetic energy and potential energy. However, it is often assumed the system is stationary, so the kinetic energy and potential energies of the system are ignored. The change in the internal energy between the initial and the final stage equals the net energy change, energy transfer by heat, subtracted by the net energy transfer by work. So Q and W indicate the net energy transfer by heat and work, respectively. So Q is Q in minus Q out. So some heat goes into the system and some heat goes out of the system. W is W out minus W in. Some work is done by the system and some work is done on the system. So our assumption is Q is positive when heat is transferred into the system, and W is positive when work is done by the system. How to evaluate the internal energy? Let's take water as an example to see how we evaluate the internal energy during a process. So here are three cases, depending on how the phase of water changes. The first case, water exists in a single phase, either vapor or liquid. The internal energy is expressed as the product of mass times the specific internal energy. Second case, water vapors turns into a two-phase liquid-vapor mixture. Part of the system is saturated vapor with mass mg. Part of the system filled with saturated liquid, mass mf. So mass of the liquid may be different from the mass of the vapor. So the total internal energy is the sum of the internal energy of the liquid water and the internal energy of the water vapor. So it can be expressed as m liquid, mass of the liquid, times specific internal energy of the liquid, plus mass of the vapor times specific internal energy of the vapor. The third case, the mixture of two separate masses of water vapor. The prime symbols and double prime symbols indicate two separate regions. Initially, it was at different mass, different temperature, and different pressure. After mixing the two, the total mass is simply the sum of the two masses. T2 and P2 indicate the temperature and pressure at the final state when the system reaches equilibrium. We'll take a look at examples for each case, and let's see the first example. Example 3.3. A well-insulated rigid tank having a volume of 10 cubic feet contains saturated water vapor at 212 degrees Fahrenheit. Well insulated. There is no heat transfer across the system boundary, so we can say Q is 0. Rigid tank indicates it has a constant volume. There is no boundary work. Since it is a closed system, the specific volume is also a constant during a process. Temperature is given 212 degrees Fahrenheit, and the quality is given saturated water vapor, so quality is 1. So two independent intensive property fix the state. The water is rapidly stirred until the pressure is 20 pounds per inches squared. Determine the temperature at the final state in degree Fahrenheit and the work during the process in BTU. So we are going to assume the gas is a closed system, no mass cross the system boundaries. The initial and the final states are at equilibrium. There is no net change in kinetic or potential energy. The system is stationary. There is no heat transfer with the surrounding. Q equals 0. The tank volume remains constant. Since it's a closed system, we can also say that specific volume of the system remains constant during the process. So first, let's fix the state. First, state 1. We have a saturated water vapor, so quality is 1. And the temperature is given 212 degrees Fahrenheit. Two intensive independent property fix the state. So we can determine the other properties. So see table 8.2e. This is saturation table for water. At 212 degrees Fahrenheit, the specific volume of saturated vapor is 26.80 cubic feet per pound, and the internal energy of saturated vapor specific volume is defined volume over mass. Mass of the system can be calculated with the knowledge of volumes and specific volume. Volume is 10 cubic feet. Specific heat of the saturated vapor so mass of the system is determined. State 2. We also need two independent intensive property to fix the states. Pressure at state 2 is given. And we also know that the specific volume at state 2 equals specific volume at state 1. As the volume and mass of the system remain constant. So we can fix the state. We want to determine the temperature at state 2, but we don't know if it is saturated water or superheated vapor. So let's see the saturated water table first. At 20 psi, the specific volumes is between 0.1683 and 20.09. But the specific volumes we calculated at state 2 is 26.80, which is greater than the specific volume of saturated vapor. So it suggests that the phase at state 2 is superheated. So we need to see table 8.4e. So at 20 psi, specific volume of state 2 is 26.80, which sit between these two. So we expect the temperature is in between 400 and 500 degrees Fahrenheit. So we need to do the linear interpolations to determine the temperature. So add V2 do the linear interpolations, temperature was determined. We also want to determine the internal energy at state 2, which sit between these two numbers. We do the linear interpolation again. We apply the energy balance to the closed system, delta U the system considered to be stationary. We ignore kinetic energy change, potential energy change. The system is well insulated. Q is 0. So W and system only contains water vapor. And mass of the system was calculated. And let's go back to TV and PV diagram. So we fix the states as state 1 and state 2. State 1 is at saturated vapor, so we know that it's on the saturated vapor line. So let's say this is state 1. State 2 has the same specific volume. So the process moves straight up and the temperature increases from 212 Fahrenheit to 445 degrees Fahrenheit. So we'll have a vertical straight line. On TV diagram, we can draw the similar process. State 1 on saturated vapor line and specific volume remain constant, but temperature increases from 212 to 445 degrees Fahrenheit. And we need to note that on PV diagram, this is the constant temperature line. On TV diagram, this is constant pressure line. Example 3.4. Water contained in a piston cylinder assembly undergoes two processes in series from an initial state where the pressure is 10 bar and the temperature is 400 degrees Celsius. The system is a piston cylinder assembly, so typically in the piston cylinder device, the volume of a system may be expanded or compressed during a process, so it involves the moving boundary work. Process 1-2. The water is cooled as it is compressed at a constant pressure of 10 bar to the saturated vapor state. Process 2-3. Water is cooled at constant volume to 150 degrees Celsius. So we need to sketch both processes on TV and PV diagram. For the overall process, determine the work in kilojoule per kilogram. Typically, the unit of work is kilojoule, but it asks us to determine the work in kilojoule per kilogram. For overall process, determine the heat transfer in kilojoule per kilogram. Also, the typical unit of heat transfer is kilojoule. It asks us to determine the heat transfer per unit mass. So we are going to assume the system is a closed system and piston is the only work mode. It involves moving boundary work. There are no changes in kinetic or potential energy. So first thing what we will do is to fix the state. State 1. Pressure is given 10 bar. Temperature is also given 400 degrees Celsius. So two independent properties are known, so we can fix the state. Table 8.4 is a superheated water vapor tables. So pressure 10 bar and temperature 400 degrees Celsius. We need to know the specific volume and internal energy. State 2. Pressure is given 10 bar and is in the saturated vapor state. So quality at state 2 is 1. So two independent properties are known. We can fix the state. So use table 8.3, properties of saturated water. At 10 bar, specific volume and temperature, saturation temperature, only moving boundary work exists in this problem. So work, this is the moving boundary work. Since work is a path functions, so the work depends on the path how the process is conducted. So we can take the integrations from 1 to 2 and 2 to 3. Process 2-3 is conducted under constant volume. So these terms cancels out. And pressure is constant. So we can write P times V2 minus V1. Divide the equations by the mass of the system. Pressure 10 bar, V2, V1, and be careful of the unit. The work is negative 112.2 kilojoule per kilogram. So our assumption is work is done by the system is positive. And the result is negative values, which means the actual work was done on the system. And state 3. Temperature is given. And process 2-3, water is cooled at constant volume. So V3 equals V2. So two independent properties are known. We can fix the state. 150 degrees Celsius and the specific volume at state 3, 0.1944, which sit between these two numbers. So we can calculate quality of state 3. Quality at state 3 From the quality, we can also determine the internal energy at state 3. At 150 degrees Celsius, internal energy of saturated liquid, internal energy of saturated vapor. And determine the heat transfer for the overall process. Apply the energy balance equations. Internal energy is a property. Property is a point function. So it does not depend on the path. So the internal energy change is the final state minus initial state. Divide both sides by m. So negative sign here also indicates the net heat is transferred out of the system. So we also need to draw the process on PV and TV diagram. State 1 is at superheated region, so it's right hand side of the saturated vapor line. So let's say this is state 1 at 10 bar and 400 degrees Celsius. Process 1, 2. Water is cooled as it is compressed at a constant pressure of 10 bar. So this is y-axis, represent pressure. So state 1 to 2 moves along the horizontal line. And state 2 is saturated vapor state. Quality is 1. So it lies on the saturated vapor line. So state 2 is here. And process 2 to 3, the water is cooled at constant volume. So process was conducted under constant specific volume. So it's a vertical straight line. And state 3, we have a saturated mixture. On TV diagram, state 1 is in the superheated vapor regions. Process 1, 2 go through a constant pressure. So remember, this is the constant pressure line. So it moves along the lines and stop at the saturated vapor line. From state 2 to state 3, it undergoes a constant volume process.